Hey everybody, Dr. White here with a little run through of section 1-1 of the textbook, Properties of Probability. So, of course, you always read the textbook yourself, but you can use this screencast as a way of breaking into it, or you can stop the screencast and be looking at it and reading along with the textbook as you watch the screencast and getting those sort of extra rich details and scribbling things for yourself, just like I'm scribbling here in my notes. So as I looked into it, I saw that there were some important definitions at the beginning. The definition of a random experiment, okay? Oops, I don't know if you can see that, but a process whose outcome cannot be predicted with certainty. So for example, an example of a random experiment would be, flipping a fair coin 3 times, because you can't predict with certainty how those flips will land up, heads or tails, Now, the next important concept involved with the random experiment is sample space. Now, that's just defined to be the set of all possible outcomes of the random experiment. So, for example, with the tossing the fair coin 3 times, the sample space, which we usually call S, is a set of 8 things. The 8 things are just little, they're called outcomes. Everything in the sample space is called an outcome. And each outcome is supposed to be like a way that the experiment could have come out. I've got the outcomes kind of coded here with T's and H's. So this outcome right here, TTT, stands for tails on first flip, tails on second, tails on third, okay? And then there's 7 other outcomes. So there's heads and then 2 more tails. And here's tails, heads, and tails. And you'll see that I'm kind of systematically going through getting myself more and more heads each time until finally I come up with all heads. And that's easy for me to realize, oh, I'm done here. This is all there is, just these 8 outcomes. So that's the sample space. A next important concept is that of an event. An event is any subset of the sample space, okay? Any subset of the sample space counts as an event. So here are some examples. Hey, the empty set, which you could represent with, like brackets and nothing between it. That's a set. It's a subset of the sample space because the empty set is a subset of every set that there is. So it's an event, and we call it the empty event. You could also think of it as like anything impossible, like getting 4 heads would be impossible in this setting. So you could think of that as the empty event, or getting 18 heads, or getting -2 heads, or getting 35 tails, or whatever. The entire sample space is an event because every set is a subset of itself. So the sample space is a subset of the sample space. You can think of that as, well, something has to happen, So that's the event of anything happening at all. Here, what we think of as intuitively as the event of getting 0 heads can be written more formally as the set whose only element is the TTT, That would be a perfectly good event. Now, if you know a little bit of set theory, you know that if there's n things in your set, then there's 2 to the n subsets of that set. And there's 8 things in S, therefore there are 2 to the 8 subsets, 2 to the 8 possible events for this random experiment. Okay, next important concept is the probability of an event, okay? So let's let A be any event at all associated with some random experiment. the probability of A, which we write P with A in parentheses, is going to be some number anywhere from 0 to 1. And we're going to adopt, kind of roughly adopt, what is called the frequentist notion of probability. And the frequentist notion of probability is that the probability of an event should be what the proportion of times that that event would occur if you were to repeat the random experiment many, 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 many times. A little bit more formally, it's like this. Imagine you're going to repeat the random experiment n times, okay? Where n is some big number, okay? And say you compute the proportion of times the event occurs. So you count the number of times that A occurs and you divide by the n. That would be the proportion of times that A occurs. If you were to somehow take the limit as n goes to infinity of such proportion, then you would get the probability of A. Okay, so that's the frequentist notion of what the probability ought to be. And we got a little separate screencast where you work a little bit with R in the RStudio environment to try to get a feel for how these long-run proportions, really do work out to what you intuitively consider to be the probability. But for now, we'll just use our intuition a lot of times to assign probabilities to events. So let's use some intuition in the example that we've been working with, the random experiment when you're flipping a fair coin 3 times. So what I've got here is a table with 2 columns, okay? And the first column is all of the outcomes. And so that's your sample set, right? A sample space. And over here is my assignment of probabilities to each of those little singleton events. Like the probability of getting tails, 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 I say is 1/8. And I say that for each of the other singleton events whose only element is, the one little outcome. So why am I doing this? Well, and I'm thinking, it's a fair coin, so T or H is equally likely. So it would seem to me like each of these outcomes would be equally likely. And there's 8 outcomes, and together they make up the whole sample space, so I figure they should be each 1/8. So that's my intuition at work. But once you've got that intuitive idea set up for each of your outcomes, then you can bring in sort of other intuition. Like say you're thinking like, what's the probability of getting 2 heads? Say you want to know that probability. Well, what you do is you look at the set of outcomes that truly constitute that event. And that's this little set right here, right? The ones where you get 2 heads. And so that's 3 things. 3 out of the possible 8. And so you would say 3/8. That's the equal likelihood principle at work. Equal likelihood principle. So it's something you'll use quite a lot because when you compute probabilities for events, because quite often in your intuitive work, each of the outcomes is going to be equally likely. Now you'll notice that 3/8 is the same as the sum of these probabilities right here, and that's no accident, and we'll see why in just a wee bit. Here comes the wee bit. Let's set up a little bit more theoretical framework so that we can jazz up our intuition with more mathematical reasoning. So let's have another go at the definition of probability, but more from the point of view of set theory than from the point of view of this idea of long run repeating the experiment a lot of times. So in this definition, the probability is not like the probability of any one thing. Probability is going to be a real valued set function P that assigns to each event A associated with the sample space S, a number P of A, okay? And then it's going to satisfy some conditions that we've got down later. But I want you to stop and think about this. P is actually a function, and its domain is not numbers. Its domain is the set of all events. So like in our example, it would be that set of 2 to the 8 events, you know. And for each one of those events, it returns a number that's the probability of that event, okay? And so this example that we had up here is the function P at work returning a number, 3/8, for this event, the get two heads event. But it's got like another bazillion, 2 to the 8th minus 1 things to tell us, about the probabilities for the other events. Now, so there'll be a lot of information in one of these functions. It's doing a lot of work. But the definition says it's got to have these general properties, okay? First of all, for any event at all, it's only allowed to assign a number that could be as small as 0 and as big as 1. And anything between is also possible, but not outside of that range. The probability of any event has to be between 0 and 1, or we are not going to call this a probability function. Furthermore, that special event, the sample space itself, has to be assigned probability 1. P of S has to be 1, or I'm not calling this a probability function. And thirdly, condition C here, if you've got, say, n events, A1, A2, up through AN, and if they've got the property that any two different events intersect in the empty set, what we call mutually disjoint events, if you've got n mutually disjoint events, then think about the union of those events. That's another subset of the sample space, so it's another event. So it's got to have a probability P, right? That probability has to be the sum of the events, the probabilities of the events themselves. Now, the union could be read as or, because to be in the union of two things, you're in one or the other, or possibly both. So the way I would say this is that when your events are mutually disjoint, the probability of A1 or A2 all the way up to or AN occurring is the sum of the chance that A1 occurs plus the chance that A2 occurs all the way up to the chance that AN occurs. Part of rule C is that the same is true for an infinite set of mutually disjoint events. So if you had like A1, A2, A3, and so on forever, the probability that at least one of them occurs is the sum of the probabilities that they occur. Again, they got to be mutually disjoint. So that's the third condition. And any set function on the set of events that satisfies those three conditions is called a probability function. So if you got a random experiment, you actually could have lots and lots of different set functions, that would satisfy these three conditions, and they would count as probability functions by this definition. But only certain ones of them would be ones that you might use to actually model a real chance situation in your life, okay? So just because something mathematically satisfies these conditions doesn't mean it is a practical model for a real life situation. Now let's see how valuable this approach is. It's valuable because it's thinking explicitly about how events are subsets of the sample space, and so events are sets. And so then you can bring in like all your set theory to prove more things about probability functions, and they're called laws of probability. And so this really lets you ramp up your intuition and figure out more stuff than you could use with just straight up ordinary, common sense. So there's a number of things in the book, laws of probability, that are proved off of the definition of probability. And the first law of probability, theorem 1.1-1, I think they call it, the chance that, to take any event A, the chance that A occurs has to be it has to be 1 minus the chance that it does not occur. The A prime there, that stands for the set of all things that are not in A. It's the complement of A. So you could say probability of A is 1 minus the probability of not A. Might be how you could say this to yourself. Now, you can actually prove this. This is still very much common sense. I mean, you would think I don't need to prove. I mean, ever since we were very young, we knew that if there was a 70% chance of rain, then there had to be like a 1 minus 70%, 30% chance of not rain, right? But you can actually prove this using set theory plus the definition of probability. And that's what makes math so fun, partly, is that you can prove these things that you already thought were obvious. So check this out. Here's how the proof goes. The set S is actually equal to the union of A and A complement, because every outcome is either got to be in A or not in A, right? Pictorially, with a Venn diagram, where S is this entire rectangle here, and A is this circle, so all the points inside the circle make up the event A, then A prime, the complement of A, is all of the points in the rectangle that are not in the circle, okay? And the S is hanging around outside saying, hey, that rectangle is everything, all the outcomes. Now, S is A union A prime, but notice that A intersect A prime is the empty set. There is no outcome that is both in A and not in A. Now, we can make use of this. Let's check this out. We know that 1 is the probability of S. Why? It's because of part B of that definition. Probability of S had to be 1. Okay, but S is A union A prime. So the probability of S is equal to the probability of A union A prime. But A and A prime are mutually disjoint events. They're intersected in the empty set. So by the third part of the definition, the probability of the OR of them has to be the sum of their probabilities. Putting this all together by transitivity of equality, we get that 1 is equal to P of A plus P of A prime, okay? And so then we just have to solve for P of A, and we get the law that we were supposed to prove. We are done. So that's really cool. You can use the set theory to back up, totally formally prove this intuitive idea about probability that you've had for a long time. Another kind of intuitive idea you might come to once you intuit the empty set is that the probability of the empty set should be 0. The probability for something impossible should be 0. But we can prove it. How? Well, notice that the sample space is the complement of the empty set. It's everything that's not in the empty set, right? And so thinking back to this law that we've just proved, the probability of the empty set should be 1 minus the probability of its complement. So this is important. As soon as you prove a theorem, it goes into this bag of tools that you can use to prove other theorems. You don't have to keep going right back all the way back to the definition. You can also use theorems that you've proved about the concept. Okay, so probability of the empty set is 1 minus probability of S. But the probability of S is 1 by part 2 of the definition of probability. So the probability of the empty set is 1 minus 1. Therefore, the probability of the empty set is 0. Kabam, kabam, kabam. The invincibility of logic brings us step by step to our conclusion. Wonderful. Okay, here's another intuitive idea that can be totally backed up with set theory. Take any events A and B. If A is a subset of B, so like if anytime A happens, then B has to happen, then the probability of A had darn well better be less than or equal to the probability of B. I don't give the proof here, look in the book, but you can use set theory to totally nail that down. You can also nail down that the probability of A is less than or equal to 1 for any event A. And so that's the theorem 114 in the book. You can look at the proof. Intuitively, along with these laws, you should have pictures in your head, little Venn diagrams in your head that help you remember them and keep working with them. So for like law 3, I'm drawing my sample space as this rectangle. I'm drawing A as this little circle and B as a possibly bigger circle of stuff that contains it. And you start thinking of the probability of an event as the area contained within the little boundary for the event that you drew. That's really important way of understanding probability. Is going to be really useful for you later on. Probabilities are areas, and the biggest possible probability is the area of the S rectangle, which is a 1. Okay. Something that does not occur to people like immediately when they start thinking about probability as little children is theorem 5 here. For any two events A and B, the probability of A union B is not the probability of A plus the probability of B. Not all the time. A and B might not be disjoint. And so part C doesn't just give you right away that it's probability of A plus probability of B. But it is actually always probability of A plus probability of B minus probability of A intersect B. And so you can check out the proof in the book. The Venn diagram you should have with you, though, is S. And then, here's your A circle, and here's your B circle. And if you threw those two circles together, then you'd be throwing that little intersection part, the A intersect B here in the middle, you'd be throwing that in twice, and that's too much. So you can sort of see why maybe you have to subtract out the probability of A intersect B to make up for that. But do hit the book and watch how that plays out formally with set theory, okay? There's a theorem 6 that asks you what's a formula for the probability of the union of 3 events. What's the probability that A or B or C would occur? And it's this complex thing here, okay? It's the sum of the 3 probabilities minus the probability of each of the 3 ways of intersecting 2 of the events at once, plus the probability for the only way to intersect all 3 of them at once. And so that's a lot. And so about the only picture you can have in your head really is this very simple diagram, that looks like the Olympic rings with 3 events, A, B, and C. And I'm going to give you an informal proof here. You're going to give the formal set theory proof as an exercise. They give you a hint in the book to get you started. And you can use that hint plus remember previous laws, and number 5 is going to be an important one for you to get the formal proof for number 6. But this informal proof should also feel convincing to you. So here's my informal proof. What if the probability of A union B union C were just the sum? Well, there would be a problem with that. Check out this little miniature Venn diagram here. How many times is each of the little regions determined by my borders actually being thrown in when you do this sum? Well, when you throw in A, throw in B, and throw in C, you are throwing in the stuff that's in A, but that's not in the other sets. That's the stuff over here that I'm labeling 1. Okay. And And the stuff that's in B and is not in the other two sets is also being thrown in, you know. Same for the stuff that's in C but's not in the other two sets. But you are throwing in everything in A. So like you're throwing in the stuff that's in A and in C, but not in B. However, how many times are you throwing it in? Because you're throwing in A and you're throwing in C, you're throwing it in twice. So I got this number 2 in that region. Similarly, this region here, the stuff that is in A and B but not in C, got thrown in twice. And this region here, the stuff that's in B and C but not in A, got thrown in twice. Too many times. And this stuff that's in A and B and C, it got thrown in 3 times when you threw in A, B, and C. So a lot of stuff got thrown in too much. This answer in general is going to be too large. So we got to make up for that. We got to take away those things that got thrown in too much. Okay, so what would happen if we took away from that sum these 3 things? Okay, so like say what happens when we take away A intersect B. So that's this little part right here. All right, it's the A intersect B is this 1 and 0 thing here put together. When we take that away, then we're only counting this little part once, you know, and we're going to be, and similarly, when we take away like the B and the C, we're counting this little part once, and we take away the A and the C, then we're counting this little part once. But the problem is when we did each of those 3 takeaways, we were taking away the A intersect B intersect C. So originally it was in there 3 times, but now it's in there 0 times. So we're not quite there yet. We need everything in there 1 time. So we just make up for that. We add in the A intersect B intersect C, and then everything's in there once, and it's just right. This way of thinking is called the inclusion-exclusion principle. And it's a very useful way to think about some things in elementary probability theory. In fact, I wonder if you could use the inclusion-exclusion way of thinking to conjecture what would be the law of probability for the probability of the union of 4 events. Give that some thought. Maybe we can discuss that sometime. Okay, that's the main content of section 1.1. We want to try a few sample exercises to apply it, and I'll do that in a separate screencast. You should go, like, get a cup of coffee, relax a little bit before coming back to this stuff. See you soon.